Hello everyone, in this video we're going to go over the mechanism of a very specific type of intermolecular SN2 reaction. So let's say that we have this molecule and that we're going to react this with sodium hydride. What would be the outcome? So in this scenario, hydride is a very, very strong base. It's very unstable because its negative charge is concentrated on a single proton, single hydrogen atom. So it's going to attack the hydrogen this oxygen has, and then it is going to take it. So oxygen would get the electrons. So in this case, the intermediate is going to be the oxygen with a negative charge, and it's missing a proton. So now this oxygen can act as a base or a nucleophile, but it needs to do that on an electrophilic atom. But in this molecule, we don't have any other reagents. What exactly is it going to attack? So where is the electrophile? It's actually going to be in the same molecule. So this carbon here can act as the electrophile because it's attached to this chlorine. Chlorine is more electronegative than it, so this carbon is going to have a slight positive charge, and the negative charge of this oxygen can come in and attack the carbon. So what we can get is that the oxygen is going to attach to that carbon. What you will notice is that this will form a ring. So in order to draw the ring properly, I suggest that you give it numbers. So the nucleophile, say that the oxygen is 1, this carbon is 2, this carbon is 2, this carbon is 4, and this carbon is 5. Now keep in mind that when the oxygen attacks, the chlorine is going to leave. That's the leaving group. So once this occurs, we're going to write the oxygen, and that's number 1. So we're going to draw the other stuff. So this is carbon number 2, and we're going to have carbon number 3. And carbon number 3 has a methyl attached to it, like this. So just carbon number 3 with a methyl attached. Then we're going to have carbon number 4. Then we'll have carbon number 5. And carbon number 5 is going to bond to this oxygen due to the attack of the oxygen like this. So there's a bond between the oxygen and the number 5 carbon. So this will be the outcome. So if you redraw the molecule without the numbers, it'll look like this. Let's go over a similar problem. Let's say we have an iodine atom here, and there's also a chlorine here, and we have an oxygen right there with a methyl here. And we react this with sodium hydride. Sodium hydride will come in and attack the hydrogen. And the hydrogen will combine with the hydride to form hydrogen gas. Then that'll just go out of the solution. So that step is irreversible. So from this first step, we get a molecule, we get hydrogen gas going off. But we also get a molecule that looks like this. Now the oxygen is the nucleophile. It's going to attack an electrophile in the same molecule again. But notice here that we actually have 2 electrophiles. We have this carbon, which is attached to the chlorine, and we have this carbon, which is attached to the iodine. Where is this oxygen going to attack? Is it going to attack here, or is it going to attack here? So we can write the outcome of both of those cases and see what would happen. So let me delete this so we have space. If the oxygen were to attack on the carbon containing the chlorine atom, we would get a ring that is 1, 2, 3, 4, 5 members. It's going to have an oxygen, with the rest of the members being carbons. And carbon number, or atom number 1, 2, 3 is going to have, so 1, 2, 3, we're going to have here a methyl group. And the last carbon, which is this one, is going to have an ethyl and an iodine atom. So this is the outcome that we get by doing that. Now let's try the other scenario. Let's have this oxygen attack the carbon containing the iodine. What would happen in this case? So here, we're going to get a 1, 2, 3, 4, 5, 6 membered ring. And carbon number, or oxygen number, well, atom number 1, 2, 3. So 1, 2, 3 is going to have a methyl group. And then not number 6 but number 5. So 1, 2, 3, 4, 5. That atom is going to have a chlorine on it. I should draw the leaving groups leaving as well. This will occur, and then this will also leave. Now, which one would form more often? Would this form more often, or would this form more often? The answer is that we're going to get this outcome happening more often. That's going to be the major product, and this will be minor product. Now, the reason is twofold. So, for one, 6-membered rings are more stable than 5-membered rings. So, this is 6-membered, and this is 5-membered. And so 6-membered rings are going to be more stable. Now, the other reason is that the oxygen atom here is attacking a carbon where the leaving group is chlorine, right? But here the leaving group is iodine. Now, which one is a better leaving group? Which one is it easier to attack and throw off the leaving group? So the iodine is going to be a better leaving group than chlorine. The reason is because once the leaving group leaves, so once the chlorine leaves, it's going to form a chloride ion in the solution. And once the iodine leaves, it's going to form an iodide ion in the solution. And the chlorine ion is going to actually be a lot less stable than the iodide ion, even though the electronegativity might tell you otherwise. Iodide is a very large atom. If you look at the periodic table, it has it's a lot of protons and neutrons. So this negative charge is going to be spread out over a larger space than if you were to have the chlorine spread out over a small area. So the outcome of kicking off the chlorine is more stable than the outcome, is less stable than the outcome of kicking off the iodine. Therefore, the iodine is going to be kicked off more often, meaning this will also occur more often because of that reason.